So today we'll just begin with the discussion of ADC. So yeah, in the last class we discussed about DAC characteristics, and we just pulled out few of the parameter names like VLSB and uh, full scale voltage definitions and VMSBs. And later on we just had a characteristic graph reflecting all those set of graphs in them. And yeah, so before I really start up, I just want to just have some diagrams or pictures to be open. So just give me a second. I'll just try to open that so that it becomes easier for me to copy and paste. Yeah, got them. Yeah. So there is a bit of syncing issue with my notes. Just a second. Yeah. Yeah. So let me begin our class. So with the discussion of ADC, and as we know that this ADC is the one that performs a conversion from analog to digital conversion. So to digital converter, and it can be shortly called as uh, ADC, and we'll just look into the characteristics as well as the input output relation. Okay, so along with the block diagrams, but generally an ADC actually converts a signal which is analog, and it has a characteristic that these signals are infinite valued. Okay. So it's an infinite valued input, and this infinite valued input, which is in terms of analog, has to be converted into a finite quantized digital codes. Okay. So during this process of converting this infinite valued signal to a finite quantized digital codes, uh, what happens is that there is a range of values. Okay, so there is a specific range of values as I discussed in the last class. So those specific range of values would be mapped to a single digital code. Okay, so because of this multiple data is getting mapped onto a single digital code, it introduces an error, and we call this error as quantization error. Yeah. So and since because we are trying to convert a multiple data to a single data, uh, the process of this conversion from analog to digital is always much more difficult than the conversion of a digital data to an analog, as we discussed in the last class about the DAC. Okay, so now let me just draw a simple block diagram that would reflect. So as we have, the analog input can be either in terms of a voltage signal, or it can be a kind of current signal. So if I have a voltage input, then the appropriate reference voltage that has to be supplied supposed to be a V reference. Okay. and then the corresponding output would be in terms of a digital data. So again, the digital data can run from all the way from d naught to all the way to dn minus 1, okay, so which is the MSB bit. Yeah. So so all of these number of bits that I have is basically an n bit data that is appearing at the output. Okay, so in case if we have dealing with an input signal which is current, then the type of reference source that we have to apply would be a current, and accordingly the data would then never changes, and the mathematical relation between this analog input signal and the output, which are digital form, will be discussed later on when we discuss about the architecture. Okay, so now that let me just try to bring out the characteristics graph that tries to bring out the relation between those input signal Vin and the output signal digital data. Okay, so as I stated before, by default we will consider the analog signals to be always a voltage signal, but it can also be uh, a current signal. But as of now, we'll just hold this analog signal as our basic signal. Okay, yeah. So in order to draw the graph, I just want to pull out a picture. So yeah. So let me try to expand this picture so that it becomes much visible for you. Yeah. So in the case whenever our inputs, which are in analog form, which has been scaled along my x-axis, so whenever the value of input, which is, so this is basically Vn. Okay. So whenever the value of Vn is equal to 0, then the corresponding output voltage that we or the corresponding digital data that we need to get out of this particular architecture supposed to be equal to 000. Okay, so this is under the consideration that we are dealing with an ADC, which is a 3-bit ADC. Okay. So where I apply my input, and this is a 3-bit ADC circuit that I have, and that's end up resulting in a data that starts from 0D0 to all the way to D2. Okay. So there are basically 3 bits out of this particular block diagram. Yeah. So now if this given value of Vn is equal to 0, then the value at the output of this ADC is supposed to be equal to all zeros, right? And this is what is being mapped. And when I am just bit higher than this given value of 0, say for example, I am somewhere in the midway between this 0 by 8 to 1 by 8, which is nothing but 1 by 16. Okay, so even this value of analog input is still mapped onto the same data. Okay, so which means that even if the input that I have, that I am trying to feed, was equal to 1 by 16 of some V reference, okay, even this value is still being mapped onto the same data that we have. So even though the data is not, or the input is not exactly equal to 0, still the data we are ending up results in the same value of 000, right? So this results in what is known as a quantization error. Okay, now let me map these kind of phenomena that is happening, that a value of input, when it is beyond the value of 0, an error is being introduced. Okay, so that error is right now would be equal to 1 by 16. Okay, and until I reach the particular input value, which is exactly lesser than this 1 by 8. Okay, so all of these values would then be mapped onto the same data of 000, right? And due to which the error actually grows up till I reach the value of 1 by 8. Okay, Now the moment I reach this value of input of 1 by 8, then the output would then shift directly to a value which is equal to 000. So what I really mean here is that if the input changes from 0 to 1 by 8, now the data at the output would then change from a value of 000 to a new value of 001. Okay, so I'm just reading from the MSB, or yeah, so I think you got this particular mapping. Okay, so now in this case the value of 1 by 8 is actually properly been mapped onto this digital data of this 001. Okay, now due to which the error that happens between this corresponding input to the output is actually goes down to all the way to 0. Okay, because there is no error in it. But again, when I increase the value of this Vn beyond this 1 by 8, these values that I have will then still be mapped onto the same data. And because there is a because it introduces the same output data for any value that is beyond this 1 by 8, and for value that is less than 2 by 8, still it is all been mapped onto the same output of 001. It has an error that keeps rising, and the moment the input of my signal goes to 2 by 8, the error actually grows up. Okay, and then it directly shifts down to a value of 0, and in a way that the quantization error will then be constructed something like a kind of sawtooth waveform, which looks something like this. Okay, so hope that you're clear with this basic definition. Let me just complete this diagram or the drawing of this quantization error graph. Okay. Yeah, so in each of these cases you could see that the transfer error that we are getting out of this particular ADC is a kind of staircase waveform. Okay, so this is what we end up having as a kind of graph for us. And in order to measure or in order to put this quantization error quantity in terms of a mathematical term, I could also draw an analog signal on top of this graph. Okay, so which is nothing but drawing a straight line which actually reflects. Okay, let me use this color. Yeah, so these dotted lines that I am trying to draw in green color is basically represents the analog input, and the difference between this analog input and this step width actually represents the quantization error. So mathematically one could write this quantization error QE, okay, as Vn minus the V staircase. Okay, so hope that you're clear with this. So the Vn is the one that we have in dotted line, and the V staircase is the one that you could see that as a kind of staircase in this case. Okay, and one can also see a kind of width. Okay, and this particular width is called as an ideal step width. Okay, and we also had a similar discussion of step height when we discussed about this DAC. Okay, so let me just quickly glance through that, what I really mean by this. We had drawn a graph. Yeah, so in the case, so this is a kind of graph that has been plotted for a DAC architecture, and in the case of a DAC architecture, one would refer the step height as something like the space between the two adjacent uh, outputs. Okay, so which is nothing but the VLSB is been mapped on in terms of a step height. Okay, so you have to be clear with what I'm trying to say, and you could always see that the step height or step width is always associated with some sort of voltage terms. Okay, so something like 1 by 8 or 0 by 8, or all of these terms are being associated with this step height. In the case when I'm talking with a kind of DAC, and when I discuss about this ADC, you could find those data of 0 by 8 or 1 by 8, all of these data been appearing on towards the x axis. Okay, and due to which we call those associated with, or basically the spacing between this neighbor input values or being spaced away by one LSB. Okay, and we call this one LSB spacing as an ideal step width. Okay, so that this is something that we have to go ahead with this definition, and we will be widely using this step width and step height definitions when we discuss about some sort of nonlinear errors. Okay, yeah. So hope that the mathematical expression for this quantization error could be expressed something like this, and we can also rewrite this V star case, okay, the step voltage in terms of the digital data, which is again denoted in terms of the decimal equivalent value of the digital data multiplied by the V reference divided by 2 to the power n. So again, the ratio of this V reference divided by 2 to the power n is nothing but our VLSB quantity. Okay. So if for example I just want to measure the step width or the staircase of this particular quantity or this particular, sorry, yeah. So in order to evaluate this step or this staircase, I have to know what is the number that is associated with this, so which is basically 2. So what you would get is something like 2 into the VLSB, and the VLSB for this 3-bit ADC is basically 1 by 8, okay, and due to which we end up having 2 by 8. Okay, so as you could see that this is the corresponding value of 2 by 8 that we are having it over here. Okay, so hope that I'm just not confusing you much. Okay, so let me just move on to the next parameter, so which is again that is related to this quantization error. So now let us try to see what is the maximum height this quantization error reaches. Okay, so what is the amplitude of this QE that I have here? So if you look carefully, the magnitude of this particular quantity is basically equal to 1 by 8. Okay, so this 1 by 8 is a term that is defined in terms of VLSB, right? So this 1 by 8 is for a 3-bit ADC, and that could be generalized to an n-bit ADC as 1 by 2 to the power n, and this quantity, if it has been multiplied by some V reference, we call that as a VLSB, or if it is not multiplied by this V reference, we call this as just LSB. Okay, so hope that you are clear. So the conversion or the difference between this LSB or this VLSB is very simple. Okay, so if I have this 1 by 2 to the power n, when it has been multiplied by V reference, we get a voltage term out of this particular quantity, and we call that voltage as a VLSB. Else, if I have just 1 by 8 or just by 1 by 2 to the power n, then we call this as a simple term as LSB. Okay, yeah, and again the magnitude of this quantization error is basically is equal to 1 LSB term, and also the range of this quantization error QE always falls between a value of 0 to a maximum value of 1 LSB. Okay. Now in most practical cases, the errors, all the errors of any data converter has to be always within the range of plus or minus a half LSB. Okay, so this is the practical conditions, and later I will just tell you like what are the other type of errors that we have. But as of now, in practice, all the errors that we have due to non-ideal components of a data converter has to be within plus or minus of LSB. Okay, so hope that you are clear with this. And so when I say all type of errors, the errors that we are talking with respect to a data converter can be a nonlinear error, or it can be a linear error. So these are the errors we will be discussing it today, and it can also be a quantization error, and this quantization error is more specific only for ADC structure, not for a DAC. Okay, So any of the errors that we are associating with this data converter has to be within this range of plus or minus half LSB. But whereas when you just see here, you could see that this quantization error is actually not falling between plus or minus half LSB, but rather it falls between a value of 0 and plus 1 LSB. Okay, so we somehow have to offset this quantization error such that this quantization error is falling between this minus half LSB to plus half LSB. Okay, so this is something that by practice it has to be converted to this particular quantity. Now the way that one could think of doing this or achieving this quantization error being falling between this plus or minus half LSB is by simply staring at this particular picture again, that is the transfer function of this particular uh, 3-bit ADC. So the way that one can achieve this quantization error is by somehow offsetting this error by half the LSB. Okay, so what I really mean is that if I could somehow shift this or make this amplitude to go all the way to 1 by 16, which is nothing but our half LSB. So 1 by 16 is written as half LSB. Okay. And then the moment I reach this the maximum value of plus half LSB, I have to move all the way down to minus half LSB. Okay. So and again when I try to reach to a factor of 1 by 8 as my input, then I have to shift back to a value of 0. So clearly you could see that there is a kind of offset that has been given, and again the error grows on, and then when it reaches the maximum value of plus half LSB, it being shooted back to minus half LSB, and then it grows something like this. Okay, so clearly I need a, a graph which is in green color, okay, rather than being defined in the red color. Okay, so we want this quantization error to be something a behavior which looks something like this. Okay, so let me just try to complete this picture. Hope that it is clear or it is visible. Let me just use a dark color here. So we just want to shift all of the errors to fall within this range of plus or minus half LSB rather than uh, 0 to 1 LSB. Okay, so now in order to get this, we have to somehow modify this expression of this quantization error. Okay, so or in short, what I'm trying to say is that we need to shift the staircase basically, so that the quantization error right now being shifted within the range of minus or plus half LSB. Okay, so within this range, if I want to move, then it is only this V staircase has to be shifted. Okay, so what I really mean is that let me just try to select the graph. Okay, so let me just try to see whether I can utilize this red graph to make this V staircase to push to a new okay, just copy it and okay, yeah, I think few lines are being shifted. Yeah, so now that you could see that I'm just trying to shift this entire staircase to a new by exactly half the LSB being offsetted. Okay, so let me just change this color later, but as of now this is what I'm trying to do with respect to my the previous staircase. Okay, so now I call this green colored staircase as the new staircase value. Okay, so somehow I have to shift this by half LSB towards the left side. Okay, so now let us try to see whether I'm getting this graph that I plotted for the quantization error. Okay, so now as you could see that when I start with the value of input which is equal to 0, the value that I'm getting at the output is basically equal to 0 0 0. So there is no quantization error at this particular point, but as I move and when I try to reach to a value which is or any value that ranges between 0 by 8 to 1 by 16, all of these values are still being mapped onto the same value of 0 0 0. Okay. So due to which I reach a maximum error value of 1 by 16. Okay. But the moment I move to 1 by 16, which is the half the LSB term, I am directly switching this output voltage, or sorry, not the output voltage, but I am directly switching the data uh, of the ADC to move from a value of 0 0 0 to a value of 0 0 1. Okay. So what it really means is that when I have a value of 0, I am getting a data output which is equal to 0 0 0, but the moment I move to a new value of 1 by 16, previously this value of 1 by 16 was ending up having the same result of 0 0 0, but right now what we are doing is when I have this new data of 1 by 16, I am just changing the data to 0 0 1. Okay. So but this 0 0 1 is the data that corresponds to an input value which is 1 by 8, but still, but before I am reaching this 1 by 8, I am pushing my ADC output to a value which is 0 0 1. Okay. So this actually pushes our quantization error towards the negative half LSB. Okay. And that is what you could see at this particular point. Okay. So you could see that there is a negative value, and this negative value of VLSB happens just because of this predetermined value for an input that is not even that is lesser than the expected output. Okay. So even for an input value of 1 by 16, we are getting an output which is supposed to be an output for 1 by 8, but even for a value that is lesser than this 1 by 8, we are still getting a value of 0 0 1. Okay. And due to which the quantization error moves in the negative direction. Okay. We get a negative value out of this. So similarly, the moment I reach a value of 1 by 8, okay, so when I feed a value of 1 by 8, which is the exact value for which the output supposed to be equal to 0 0 1, then there exists no quantization error between the input and this output. Okay. And due to which the error right now would then corresponds to a value which is equal to 0 at this particular point. Okay. So in a way that I am trying to reconstruct this graph with this new staircase, but there is something that we need to note at the end. For a value of input, okay, so you could see that there is a range of input which starts from, I guess, 13 by 16, I guess. Okay. So right from 13 by 16 to all the way to a value of 8 by 8. So you could see that there is a range of input values, or input voltage is being mapped onto a single value of 111. Okay. And due to which the quantization error that happens because of this can be reflected on this particular line. Okay. So you could see that I have moved in the negative direction, and the moment I reach to a value of 7 by 8, then the corresponding output supposed to be equal to 111, all data is being equal to 111. Okay. So when the input is equal to 7 by 8, what we expect out of this data converter, that is the ADC, supposed to be all equal to 111. So in this case there is no quantization error between the input and the output, and due to which the quantization error steps down all the way to a value of 0. But what happens if I go for beyond this particular value? Okay, when the input value is more than, sorry, when the input value is more than this 7 by 8, then still those values are still being mapped onto the same data of 111. Okay. And due to which the quantization error grows, and this growth in this quantization error is reaching all the way to a value which is greater than this predefined value of plus half LSB. Okay. So that is what we are actually having at the very end of the star case. Okay. So except for the last one, you could see that all of the errors that we have out of this condition, or all of the condition errors are always falling between those plus and minus half LSB. but except for the last one, where the maximum error that we are getting as a quantization error goes all the way to plus 1 LSB quantity. Okay. So, hope that it is clear, uh, and uh, and this is how the architecture is being constructed in order to keep all the errors, including the quantization error, to be within this plus or minus half LSB. Okay. So, now let me talk about the different type of errors that are associated with both this data converters, like both ADCs and DAC. Okay. So, this is the type of errors that are common to both ADC and DAC. So, that is the reason why I have just generally written as the type of errors in a data converter. Okay. So, basically there are two type of errors that occurs. One, we call it as static error. The other one we call it as a dynamic error. Okay. Now, let me talk about the static error. So, static errors are the errors that generally affects the accuracy of the converter while converting uh, a DC signal or a static signal. Okay. So, these are the errors that corresponds to the signal type, which are either DC or static signals. Okay. So, a DC voltage or DC current, okay, whatever it is. So, under such condition, the data converters in general have some sort of weird behavior or an kind of inaccurate readings at the output. So, we call those errors collectively as static errors. Okay. Whereas in the case of a dynamic error, uh, these are the type of errors that happens due to the or that affects the accuracy of the converter while converting a time varying signal. Okay. So, this happens while converting um, dynamic or time varying signals. Okay. So, with this let us further step down to static errors first, and then later we will just move on to the dynamic errors. Okay. Now, under the static error, as I stated, uh, these are the errors. Okay, let me just write it down. That affects the accuracy of the converter while converting a DC signal or a static signal. Okay. Yeah. So, now with this let me just try to bring out the type of or the categories of errors under the static error. Okay. So, basically there are four type of errors that exist under the static error category. The first one being the offset error. The second one is the gain error, and the third one is known as differential non-linearity error, and the fourth one is called as integral non-linearity error. Okay. So, among these four different types, the first two types are generally called as linear errors. Okay. And the next two types, which are differential nonlinear error, and in short, this differential nonlinear error or nonlinearity can be shortly called as DNL. Okay. So, even I will use this same short form as DNL whenever I am trying to refer to differential nonlinear uh, or differential nonlinearity term. Okay, and similarly, one could have a shorter form for this integral nonlinearity, which is nothing but the INL. Okay, so these are the two type of errors, and we call these errors as nonlinear errors. Okay, so the static errors can be further categorized as linear errors and nonlinear errors, and under each type of errors we have two types in them. Uh, One is the offset error and the gain error under the category of linear error, and DNL and INL errors under the category of nonlinear errors. Okay, so let me just begin with this offset error, and then we just move on to the other type of errors. So now, as I said, each of these errors are in general are related to both the type of ADCs. So both the type of data converters. Okay, so I'm going to define under each condition how to read these errors. Okay, under each different data converters, how to read these offset error and how to eliminate those errors out of the characteristic graph. Okay, yeah. So first, let me begin with the definition of the offset error. What do we mean by offset error? So basically, an offset error is defined as the difference between the nominal and the actual offset points. Okay, so now that you might have a question like, what is this meaning of this offset point? Okay, so now in order to define this offset point, I have to talk in terms of the converters, the data converters. Okay, so let me define this offset point definition. Okay, so we use the offset point definition. Basically differs with respect to the converter that I am using. Okay, so the offset point definition, and that too with respect to the DAC, it can be defined uh, as the step value when the digital input is all equal to 0 0 0. Okay, so all of the digital inputs are equal to 0 0 0, and whatever the value that we are getting at the output as an analog output value, we call that value as offset point. Okay, so let me just explain how to read the uh, the offset error out of this particular definition. Okay, just a second, I have to pull out a picture. Yeah, so hope that I could somehow pull out those pictures. Let me just try to paste it. Yeah, and yeah, hope that this particular picture is visible. And right now you could see that the offset point is something when I try to feed in a data of 0 0 0 for a 3-bit DAC, uh, one would end up having a particular value at the output. Okay, so that has been marked here as the actual offset point. But we know that when we try to feed in a data input of 0 0 0, we have to have an output value which is basically equal to 0. But rather, what we are getting, which has been marked as a blue color, is the actual offset point, and the difference between these 2 points, which is the nominal point and the actual point, is called as the offset error. Okay, so hope that this definition is clear, and the way to read out the offset point is by ensuring that the input the digital input that is fed to the data converter or basically fed to the DAC is all equal to 000. Okay. So this is the definition of an offset point, and the difference between the actual and the nominal offset point gives us the offset error out of this data converter. Okay. So now let me define the same offset point definition, but this time with respect to an ADC. Okay. So again, just writing this offset point definition, but this one is with respect to an ADC. Okay. So it is defined as the point, or basically as the mid step, just because we know that we have shifted our graph to mid values or half the LSB towards the left side. So due to which we have this mid step term, okay, mid step value when the digital. So again, note here I am talking a digital output, okay, is equal to 0 0 zeros. Okay. Yeah. So this is with the respect to the ADC, where we know that uh, ADC converts or takes in an input data or input value of an analog and splits out a digital output. Okay. So we have to read the offset point when we have a digital output of 0 0 0. Okay. So with that definition, let me again try to pull out this picture. Okay. And let me try to expand this. Yeah. So again, you could see when our digital data output of an ADC is equal to 0 0 0, nominally what we have to get is an output value that is equal to for an input value that is equal to 1 by 16, right. That is the mid value of the input. Okay. So the mid value of 1 by 16 is what we need to get, but rather if you are getting a value which is marked in orange color, we call that as the actual offset point. Okay. So generally the offset point is always read at the mid value, okay, or the not as 0 or not as 1 by 8, but 1 by 16 as the mid value. Okay. But rather than getting this green, if we are being shifted towards the right, we like a kind of orange color, we call that as the actual offset point, and the difference between these 2 points in general will give us the offset error. Okay. So hope that these definitions are clear. So let me just move on to the next one, but before that you could see that these errors that I'm talking is always related to a digital no, not digital, sorry, it is always related to some sort of analog values. Okay. So in this case the offset error is being referred with reference to 0 or 1 by 8 as its value, as the difference value. Okay. So you could see that it has been mapped onto our V out, which is an analog signal. Even here we are referring to an offset error which has been mapped onto this analog input value. Okay. So please remember that whenever we refer to an error, we always try to refer in terms of value of an analog value, but rather than, but not as a kind of digital data errors. Okay. So that is something that we always have to keep in our mind whenever we try to read the errors out of this uh, data converters transfer characteristic graphs. Okay. So next we'll just move on to the gain error. So again the definition of this gain error is defined as the difference between a difference between the nominal and the actual gain points on the transfer function. And so while reading this, the actual and the nominal gain points, one has to ensure that it is being read only after removing the offset error. Okay, which means that we have to remove this offset error, or make sure that the offset error is being corrected, and then you are trying to go for measuring the gain error. Okay, so you cannot do the other way. You cannot start reading the gain error first and then move on to the offset error. It is always followed in a sequence where you have to first read out the offset error and remove that offset error from the characteristic graph, and then later you just try to read out the gain error. Okay, so now uh, again we have to know how to read out this gain points first in order to measure the difference between the actual and the nominal gain points. So again, let me start with the definition of gain point with respect to a DAC first, and then later I will just talk, or I will try to define the definition for the gain point with respect to ADC next. So the gain point definition, and this is with respect to a DAC. Okay. Now this is defined as the step value when the digital input is full scale. So what I really mean by this full scale is something like when all of the digital inputs are equal to 111. Okay, so whatever the number of bits that you are using as a uh, DAC. Okay, so all of these input data, digital data, has to be all being equated to a value of 111. Okay, under such condition, we will, whatever the value that we are getting at the output is called as a gain point. Okay, so let me try to bring out the characteristic graph. Yeah, so clearly as you could see that there is no offset error because already it's been removed. So you could see that when the digital input is all equal to 000, we are having an output which is equal to 0 itself. Okay, so the offset error has to be removed well before measuring the gain points or measuring the gain error. Okay, yeah. So now again, as you could see that whenever we feed in an input value of 111 for a 3-bit DAC, we suppose have a corresponding output value which is equal to 7 by 8. Okay, and this is the ideal value we are supposed to get it, but rather for this input, if you are getting this green point which is currently mapping on value of so 8 by 8 which is equal to 1. Okay, then we call this particular point as the um, actual gain point, and the difference between these 2 points is what will give us the gain error. Okay, now all of these definitions what we have discussed so far is basically just the theoretical definitions, but in general we don't have any problems on this particular gain error as well as the offset error. Okay, we will have problems only on the nonlinear errors which we will be about to discuss. Okay. So now let me again try to redefine the definition of this gain point with respect to ADC. Now again it is defined as the mid value or mid step value, and as you would have guessed, uh, that mid step value is being measured when the digital output of this ADC is full scale. So again the full scale definition is having an output value of all equal to 1 and 1. Okay, yeah. So let me just try to again bring a transfer error that represents this gain point as well as the gain error. Yeah. So as you could see that whenever the digital data output is equal to 111 for a 3-bit ADC, we supposed to get a corresponding mid value of 7 by 8. Okay, so this is the value that we supposed to get for this like sorry uh, when we are feeding in an input voltage of 7 by 8, we are supposed to get a value of 111. Okay, but rather what we are getting is that when the mid value of I guess which is somewhere falling between this these two extremes, uh, which is which is somewhere between these 2 points. Okay, so or in short, it is 6 by 8 plus 1 by 24. Okay, which is quarter of the LSB term. So it is at this particular point uh, we are having the mid value, and we call this as the actual point. Okay, so the difference between these 2 points will give us a kind of error, and which is nothing but the subtraction of this particular quantity, which is 6 by 8 plus 1 by 24 minus the 7 by 8 will give us this gain error. Okay, so hope that it is clear. And next we just move on to the nonlinear error, which is with the each of the errors have a separate definitions for with respect to DAC as well as ADC. So let me just begin with the definition of DNL with respect to a DAC. Now for a DAC, a DNL is actually measured as the difference between the actual height minus the ideal step height. Okay, so this is something that we have already discussed when at the beginning of the class. Like there is something that we always talked about, this step height. Okay, so now the reason why we speak about a step height with respect to a DAC is that we know that for a DAC the input is a digital input. Okay, so the x-axis in this case will be a D value. Okay, so which is all digital data that we have, but the y-axis will be in terms of analog signals, right? So which is something like V out by V reference or some sort of analog value. And now we know that for this corresponding input we have an output value which is equal to 0 by 8, and for this value we supposed to get an output which is equal to 1 by 8. Okay, and this is what we actually do when we try to draw the transfer characteristic graph. Okay, and one could measure the height, step height, in terms of analog values. Okay, that's the reason why we it has been read as step height. Okay, yeah, so hope that I'm not confusing you much. um, Let me try to define the DNL with respect to a transfer characteristic graph so that it makes sense for you when I try to talk about it. Yeah, so here in this case you could see the step height is equal to 1 LSB. Okay, whereas in the second case the step height is, so height is something that is being measured with respect to the neighbor point. Okay, so first let me define with the definition of DNL. Okay, now in the first case we have a DNL 1 when I try to feed in an input value of 001. Okay, for this corresponding input value the DNL1 has to be defined, and it is defined as something like actual step height. So in this case, the actual step height is equal to 0 minus, so it is 0 minus this 1 by 8 will give us the, sorry, 1 by 8 minus the previous value, which is equal to 0 by 8, will give us the actual step height, okay, which is 1 by 8 in our case. So I am just reading it as 1 by 8, but ideally each of these step values has to be equal to the same 1 by 8, right. So this would be my ideal value. So let me mark this pink color in order to represent my ideal value, and probably this color to represent my actual step height, okay. And I begin with the definition of 1 rather than beginning with the definition of 0, just because there is no previous value below this 0 value to measure a height, okay. So that's the reason why we always begin the DNL with respect to DNL1 rather than starting with the DNL of 0, okay. So we don't have anything like DNL of 0 for a DAC, clear. So now that I just want to measure a DNL error which is numbered as 2. So what does it mean is that I need to measure the height when I try to read the value of this digital, when I try to feed in the digital input of 0 1 0, okay. So when I try to read, the height is always measured from its previous value, so which means that the previous value was this black dot, and the corresponding new black dot is this for the input of 0 1 0. So that height difference is actually equal to the same 1 by 8. So this could be written as 2 by 8, sorry, I supposed to write it in terms of this color, okay. So it is measured as 2 by 8 minus 1 by 8 as the actual step height, minus the ideal step height is always fixed, which is 1 LSB, and that is being written as 1 by 8. So in this case, the end result of this will also be equal to 0. So let me write this error is equal to 0, and even this error will also be equal to 0. So let me try to read out the DNL of 3. So in the case of measuring the DNL of 3, again I have to look for this digital input value of 0 1 1, and for that the corresponding point that I have is this quantity, okay. Now in order to measure the actual step height, I have to look for the previous black dot point, okay. The height difference between these 2 points will give us the actual actual step height value, clear. So in this case, when I feed in a value of 0 1 1, I am getting an analog output which is somewhere midway between this 3 by 8 and 4 by 8, and that value is basically equal to 7 by 16, okay. And that is the value that I am getting when I am feeding an input value of 0 1 1, right. So I have 7 by 16 minus the previous data, which is this quantity, okay. So this quantity has a corresponding analog output value of 2 by 8, and which is what I have to put it here. So 2 by 8 is my previous data point, and the corresponding data point that I'm, or the value, analog value that I'm getting when I feed in an input value of 0 1 1 is equal to 7 by 16, okay. And this is basically equal to 1.5 LSB, okay. Whereas on the other hand, the actual step height is always equal to 1 by 8, or it is always equal to something known as 1 LSB, okay. So this 1 by 8 is nothing but our 1 LSB. So either I can write it in terms of LSB or in terms of analog value, something like this, okay. So the end result of this is basically equal to I guess it is equal to have to do some algebra. So which is basically 4 by 3 by 16, yeah, minus this 1 by 8, okay. So 1 by 8 is again, um, it is our actual ideal step height. So when we do the subtraction, we end up having a result that is equal to plus 1 by 16, and this 1 by 16 can be mapped onto a value which is taken as half LSB, because every LSB has a value of, so 1 LSB corresponds to 1 by 8, and due to which I could write in terms of LSB or in terms of value like 1 by 16. Clear? Yeah. So we'll just try to complete this DNL calculation just with the definition of what does DNL actually mean, or how to read this DNL value out of this particular graph. Okay. So let me move on to the next one, which is the DNL of 4. So when we feed in an input value of 100, we are getting a corresponding point which actually reads an output value which is equal to 4 by 8. Okay. So it is 4 by 8, and it is not the height, actually it is just the value that we are getting, and in order to measure the height I have to subtract this 4 by 8 from the previous value when we had an input value of 0 1 1, and that value was equal to this 7 by 16, and that is what I have to write as my height, minus the ideal step height, which is always in terms of 1 by 8, or one can also write in terms of 1 LSB. Okay. And again when we try to subtract these two quantities, I guess we would end up having 1 by 16. Okay. So this quantity is equal to 1 by 16, or in terms of LSBs I can write this 1 by 16 as half LSB, and in again this 1 by 8 can be written as in terms of LSB as something like this, and at the end we have a DNL error at 4 as minus half LSB, or in terms of quantity can also be written as minus 1 by 16. Okay. So hope that I'm you're clear with these definitions. So now that let us move on to the next one for a data of DNL of 5. So hope that the space might not fit. Okay, let me use the space which is DNL of 5. So again when I feed in a value of 5, we are getting an output that is equal to 4 by 8 plus 1 by 24. So again it's a height value in terms of LSB I can write it. So the height difference between the previous point and this corresponding new point will be equal to, I'm just writing the height value again, I'm not using the actual basically I'm not trying to write the value that I'm reading when I have a digital input of 3 minus the digital input of 2. Okay, I'm not doing it, I'm directly writing the result of the height itself here, which is equal to 0.25 LSB, and we know the always the ideal step height is equal to 1 LSB. So when we do the subtraction, we end up having a DNL error which is equal to minus 0.75 LSB. And again we have DNL of 6, which starts uh, with this definition. So we have an output value which is equal to 6 by 8 minus the previous value which is this quantity. Okay. So when I try to measure the difference between these two heights, we end up having a value which is equal to 1 by 1.75 LSB. Okay. So I'm just writing only the result of it, which is equal to 1.75 LSB minus this 1 LSB. So we end up having a value which is equal to plus 0.75 LSB. Okay. So finally the last term, which is the DNL of 7, when we try to fix in, we are getting a value which is equal to 7 by 8 minus the previous value which is 6 by 8. So correspondingly the height, or the actual height, is basically equal to 1 LSB minus the actual the ideal step height, which is equal to again 1 LSB. So due to which the subtraction results in a value which is equal to 0. Okay. So hope that you are clear with this DNL calculation for a DAC, and we still have to discuss about the DNL error with respect to an ADC. Okay, so probably I'll do this in the next class. Let me stop it here, and let me quickly jump on to the WebEx. Okay, so thanks for listening.